Hello, welcome back to trigonometry. In our former adventures, we worked on solving triangles that had right angles, were right triangles, where if had some information but we're missing other pieces, we could find the remaining angles, find the remaining sides, and so forth. But all those examples were with right triangles. Well, now we're going to venture forth into solving oblique triangles, and so forth. Solving other kinds of triangles that aren't right triangles. That's what's meant by oblique triangles. And we're going to learn two ways to do this, depending on, which way we use depends on what information we're given. There's going to be something called the law of sines that we're going to address now, and then the law of cosines that we're going to address another time. Okay, so we're going to talk about law of sines, how it's derived, how to use it, and so forth. And then there's going to be a surprising result at the end about how you can use law of sines to figure out areas of to help you figure out areas of triangles too. And we'll see some examples for that. Okay. Now to see what the law of sines is, let's first sketch an oblique triangle. Okay. Actually, I'm going to end up sketching two because I want to show you that this law works in either situation. Okay. I'm going to have to touch that up in a minute to finish connecting the dots. And also if you have this. Okay. This one, I'll just finish connecting the dots there. Okay. Both of these are oblique triangles. Neither one's a right triangle. We're going to label the sides A, B, and C, and the angles A, B, C. So the angles will have capital A, capital B, capital C for either one. And then for the sides we have, across from angle A we'll have little side A, across from angle B we'll have side B, and across from angle C we'll have side C. Okay, so in either way, what we're going to do is we're going to draw a perpendicular from vertex B straight straight down towards side AC. It's going to be a perpendicular. What that means is going to make a right angle there. It's going to start at point B and then make a right angle at side C. Now if you try to do that on this triangle, make a right angle, what you end up having to do is making a little extension here. Okay, but we're going to label that perpendicular as H because that is the height of each of the triangles. All right. And then that point that's made right here, we're going to call D. Okay. Now, let's take a look at these triangles. Either one, the process is going to apply to both triangles. One of them is an acute triangle, the other is an obtuse triangle, but the process will be the same. If you look at them, we've got a couple of triangles here. Like in this situation right here, we've got 1, 2 right triangles. And in this one, we have a right triangle right here. Either way, we have a right triangle ADB. And in that triangle, since it's a right triangle, we can say that the sine of angle A equals H over If you look at angle A right here, the sine opposite over hypotenuse. Or if you look at triangle BDC, oops, you got the sine of C equals H over A. Like if you look at this one makes one big right triangle right here. The sine of C, angle C, is going to be opposite H over hypotenuse A. Like if you use the orange dots and then continue black, and then this black A will be your hypotenuse. And then also if you look over here, like at this right triangle, sine of C is opposite H over hypotenuse A. Oops. And you know what? Something wasn't making sense there. I was looking at it closer. I wonder if any of you guys caught my mistake. When I labeled this triangle right here, I don't know why I put B. Don't know why the heck I put B there and A there. That doesn't make sense, does it? Across from angle C should be side C, and across from angle A should be side A. And across from angle B should be side B. Not sure what happened there. Okay, that makes a little more sense now. It's like looking at this triangle, sine of A, this angle A, opposite H over hypotenuse C. Sine of C, opposite H over hypotenuse A. So either triangle, these two formulas work. Well, if you take the first one and solve for H, oops, let's do that in black because I was working everything in black. Take the first formula and solve for H, you'll have H equals C times sine A. If you take the second formula and solve for H, you'll have H equals A times sine C. So regardless of which triangle you're working with, if you're just focusing on the triangle on the left or if you're just focusing on the triangle on the right, H is going to be the same value. So you could set these two equal to each other. You could say, well, in that case, C sine A equals A sine C. And then you can go a little bit further. You could divide both sides by sine A and both sides by sine C and end up here. Or if instead you divide both sides by side A and both sides by side C, you'd end up with this. And that is a part of something called the law of sines. Going through and using the sine of the right triangles that we created by drawing that perpendicular, drawing that height on either triangle, we were able to get some equations here from the sine formula, the sine ratio, solve for H, and then since H is the same in either way, set those two equal, and then rework it and get something called the law of sines. And the law of sines can help us in certain cases to solve oblique triangles. Okay, now if you did this process again and worked angle B and side B in there, what you would end up seeing after you did it for all the different possible angles and scenarios is that you end up with sine of A over A equals sine of B over B, which equals sine of C over C. Or you could flip it around, say A over sine A equals B over sine B, which equals C over sine C. And then that right there gives you the law of sines. If you know two angles in one side, or if you know two sides in one angle, to set up one of these proportions, Then you can use the law of sines and finish finding everything else. Okay, so let's do some examples. Let's do an example of using law of sines to solve an oblique triangle. These are not right triangles; they're oblique triangles. All right, let's draw a triangle ABC. I'm just going to sketch it, and just to let you know, it's not going to be drawn to scale. Okay, so we'll have A, B, C. Across from angle A is side A. Make sure I do this correctly this time. Across from angle B is side B, and across from angle C is side C. Okay, let's say that we're told that angle A here is 28.8 degrees. Okay, let's say that angle C, we're told, is 102.6 degrees. Let's say that we're told side C is 25.3 inches. And we need to finish solving this oblique triangle. So that means we need to figure out what angle B is and what sides A and B are. Okay? In this particular situation here, we know a side, we know an angle adjacent to that side, and we know the opposite angle. So this is a side angle kind of case. So we know a side, and then we know an angle that's connected to that side, and that has that side as one of its rays or segments, and then we know the angle across from the side. Okay, so then we can apply law of sines to work this. Let's see, in this one, well, first of all, we can find the third angle. That's no problem because we know that the angles in a triangle have to add up to 180 degrees. So we can take the 28.8 degrees we've got there, plus the 102.6 degrees we've got there, and subtract from 180 and see what that comes out to. So when I add them together, I get 131.4, and then when you subtract, you get 48.6 degrees for that angle. So solve for angle B, got 48.6 degrees. All right. Then we can set up our ratios, our proportions, to get some of those other sides. Well, we know angle C and side C. So we can say, well, we know that sine of angle C over side C is going to equal like sine of angle A over side A. So the sine of 102.6 degrees over 25.3 inches is going to equal the sine of 28.8 degrees over whatever side A is. Essentially you have a proportion here. So you can multiply the diagonal where you know the 2 and then divide by this remainder here, and that'll give you A. In other words, you can multiply across, set the 2 equal, and then solve for A. Alright, so this problem's given in degrees. Let me check my mode real quickly here. I'm in degree mode. Excellent. It's a good practice to check that before you get started. So what I need to do is take sine of 28.8 and multiply that by 25.3. Sine of 28.8. So don't forget to close the parentheses so it finds the sine of just that. And then multiply by 25.3. And then I'm going to end up dividing by sine of 102.6. Let's see what I get. Okay, looks like probably round to 10th place, so you get 12.5 if you do that. Okay, so side A is 12.5 inches. Alright, and then we can do the same process to find side B. I like to go back to what I was given and work with that, so I'm going to take sine C over C equals sine B over B. So the sine of 102.6 degrees over 25.3 inches, that part looks the same. So now we're trying to solve for side B, so we have the sine of 48.6 degrees over B. Okay. Alright, so let's clear that and start fresh. This diagonal, I know I could find both of those and multiply them together. So I'm going to take sine of 48.6, close my parentheses, and multiply that with 25.3 inches. And then divide by sine of 102.6 degrees. And I get around 19.4. Okay. So now I have solved that oblique triangle. Okay, so that's a case with basically side angle, angle. Alright, let's do another one. Let's say we have a triangle. I'm just going to sketch it. Let's say we have a triangle. Let's draw this in black. That looks like this. Again, I'm sketching, so please forgive me for not being perfectly straight and all that kind of stuff. We've got angle A up here, B here, and C here. And then side A, side B, side C. And let's say we're told that angle C is 117.2 degrees. We're told that angle A is 28.8 degrees. And we're told that side B is 75.6 feet. Okay, this is an example of having an angle, side, and angle together. Like you have two angles and you know the side sandwiched between them. So ASA. Angle, side, angle. Okay, once again, we can find the third angle by subtracting 28.8 plus 117.2 from the 180. You know, say some of the angles subtracted from 180 will help us find that third angle. Okay, I'm getting 146 degrees for that sum, and then when I subtract, I'm getting 34 degrees. Okay, so I know then that this angle here is 34 degrees. Alright. Now if I know angle B and side B, I can take sine of B over B, or if you'd rather, you can do side B over sine B. You can flip it over. And then I can pick either one. I can either pick A or C and work with it. So let's say I pick C. I could do sine C over little c. So I got sine of 34 degrees over 75.6 feet equals sine of 117.2 degrees over c. So now it's just like earlier, this whole process. Solve for C. Okay, so in this one I'm going to be multiplying the sine of 117.2 by 75.6. And then I'm going to be dividing by sine of 34. Let's see. Sine of 117.2 times 75.6, and then I'll be dividing by sine of 34. And that should give me C. Okay, so I get 120.2. Okay, then we can do same thing for A. We could say sine of B over B equals sine of A over A. So we got sine of 34 degrees over 75.6 feet equals sine of 28.8 degrees over A. Okay. So then sine of 28.8, oops, don't forget to close your parentheses, times 75.6, and then divided by sine of 34. And you get 65.1. So then you're able to finish labeling the triangle. So now you know all three angles and all three sides. Alright, now these problems have been pretty straightforward. When we knew the side angle situation, we were able to find the third angle and then immediately go into law of sines and not have any issues. We knew angle side angle, we were able to find the third angle, immediately jump in, go for it. But if we only know one angle, let's say we know an angle and its opposite side, and know another side. When we know the one angle, we could still use law of sines, but we have to be very careful because there's going to be several situations that could occur. There could be 0 possible triangles that fit, there could be 1 possible triangle, or there could be 2 possible triangles. So we've got to be very mindful as we're working it out and making sure we know what situation's coming up and what to do about it. So I'm going to continue in the next video, the part 2 video for this, on dealing with the ambiguous cases, and then we'll conclude that video with finding area of a triangle based on the area formula and law of sines. Okay, so thank you for joining us, and please immediately join us again for part 2 of law of sines.